Uh, so I'm pleased to introduce our theme lead, Professor Eric Kerrigan, so who will be formally open the event.
Okay, great. Thank you very much, Molly. Thank you very much for all the organizers for all putting this event together. You guys are certainly kicking off the whole network with a good amount of effort. So thank you very much for that. So I'm Eric Kerrigan from Imperial College, and I'll tell you a little bit more about the Automatic Control Engineering Network, of which I'm actually the chair of the Future Mobility Grand Challenge Research Committee. And our goal is to sort of help kickstart a whole bunch of events to sort of get this kind of futuristic landscape in the future where we can seamlessly integrate all sorts of different modes of transport, right? So if you have not already heard about it, we were lucky enough for the EPSRC to give us a grant, a network grant that started sometime last year and runs till the end of next year. To get a whole bunch of people across the UK interested in control and automation together, from academics and industry, to get us to talk together, get some exciting ideas for the future, maybe get some on collaborative projects, get some funding, whatever it might be. So at least, I don't know, I think at one point I heard we got more than 300 members or something like that. So if you're not yet a member, please go to the website ukcontrol.org and put your name up. It costs absolutely nothing. But it would be really great to see you at more of these events in the future. So the Automatic Control Engineering Network, we've got a number of sort of subcommittees. There's sort of four main Grand Challenge research committees. So there's the AI and data one, that we've got at the top left here. Then we've got a clean growth one, an aging society, and then the future mobility one that I'm chairing. So there's obviously a lot of overlap between them. So, we want to have clean growth in future mobility as well. And obviously there's a lot of AI and data happening in future mobility. So, we're hoping to see a lot of interaction across everything, all these different committees. Right. So, yeah, you guys have already, the Early Career Research Committee has already been organizing a number of really exciting webinars, and I'm really looking forward to hearing the rest of the talks today. But also, each of these committees are organizing a number of workshops over the next year or two, shall we say. And the first one that's really coming up that if you've not yet already heard about it, is the annual forum. We'll have an annual forum, obviously, but the first one this year is going to be on the 24th of March. For the Future Mobility Committee, we've been organizing an industry workshop, which will take place in May in Cranfield. The exact date is to be confirmed, but it'll probably be the 7th of May. And there, what we'll be doing is trying to hear from industry what they see as the big challenges, where we want to go in the future. And then in September, we'll have a sandpit workshop that will sort of mostly be, we think, probably driven by an academic group. And then over the next year and a bit, we'll be hosting a number of sort of roadmap workshops to put together effectively a white paper on where we see control engineering going in the UK over the next decade, 2 decades, however long. And also a number of grant writing retreats as we see the need for that. But yeah, so let's just, today we're going to focus on future mobility. And I think, as many of us already know, there's all sorts of interesting, exciting challenges and opportunities there, really looking at sort of how we can interconnect all these different modes of transport, so there's seamless integration going, say, from here to somewhere else in the UK via various modes of transport. That just happens nicely and easily. That all of these journeys are ideally net zero, so electrification clearly plays a big role in probably all the sectors in one form or the other. AI and self-driving vehicles, and that is all becoming a really exciting area. The future's already here. It's just a matter of making it cheaper and probably a little bit safer as well, and getting societies to sort of accept a lot of this stuff that's out there. But yeah, we are here as the Automatic Control Engineering Network to get together people from across a variety of disciplines, because we'll really need people from not just the control engineering community, but also related communities such as computer science, robotics, and working together to help create this. And so that's really what we're hoping to do over the next few years. So that's enough from me. Okay, over to you, Bolly.
Thanks, Eric. All right, okay, let's welcome our first speaker. So Dr. Jingyu, he's currently a reader at Loughborough University, and his research interests include control theory and application to autonomous and electrical vehicles. Okay, today he's going to present on safety critical control under disturbances, the control barrier function approach.
Okay, thank you, Polly, for your introduction and your invitation. So yeah, good morning, everyone. So it's my great pleasure to participate this very interesting and important activities. Okay, so my name is Junyang. So I worked in Loughborough University. Today, I would like to share some of my our works on safety critical control under disturbances. So we're trying to use a control barrier function approach to address the problem. Okay, so here's the contents. So the first part is about the background. So on the safety critical control. I think the main motivation is the intensified pace of intelligence revolution. So in robotics and autonomous systems, we have like contact-rich scenarios, like in the surgery robots. The robots will have physical contact with human, and also in industries like the autonomous brain system is critical to like have bowling guard during the operation process. Also, in drones, the collision avoidance is a very basic concern in the system. The second, basically we will do some literature review and give the motivation why we recommend control barrier function approach. I think the most popular approach to like guarantee the constraints is a model predictive control. So by like take the safety constraints as a normal constraint for the optimization problem. So MPC is a popular approach to like guarantee the constraints for the dynamic system. The advantage is it's quite easy and straightforward to design and implement, and the disadvantage is has a poor computation efficiency with non-linear systems and non-linear constraints. And the second approach to achieve safe control could be reachability analysis. And the basic principle is, so if you give the initial set of the dynamic system, with the model, you can calculate the reachable set. And finally, you can verify the intersection between the reachable set and the unsafe set to like check the safety of the system. So this one is quite intuitive, but for like continuous system or is quite the computation is quite complex. And third category is barrier level function, or sometimes we use the method called prescribed performance control. So in this approach, normally we use a nonlinear gain, a nonlinear function or nonlinear gain in the control system. So the basic principle is if the system state approach to the boundary of the system, so there will be a high gain to drive the system away from the boundary. So the advantage is it can combine the stability and the safety together during the design. And the downside is the design complexity is quite high, and also you need to have customized design for particular system. And the original barrier function has a singularity problem because you use a gain which can tends to infinity when the states approach the safety boundary. So so here we try to use a control barrier function because the control barrier function have some advantage. I think the most distinguished advantage is property of correct by design. So that means the safety is guaranteed by rigorous theoretical mathematical rules. And the second advantage is quite like computational efficient for nonlinear system and complex nonlinear safety constraints, because using control barrier function, you can translate the like the long convex optimization problem to a QP problem. And compared to the barrier lab function, it doesn't have the singularity problem. And the last, the design is quite flexible, so we call it a patch feature. So which means the control barrier function can be combined with any feedback controller. Like I think the most popular control approach is reinforcement learning. It can be used to guarantee the safety of the reinforcement learning approach. So the third part, I would like to introduce some foundations of control barrier function-based safety control. So here's in this slide, we introduce some basic definitions for control barrier function. So we consider a fine nonlinear systems. We have the like the safety set, which is denoted by C, and the partial C is a boundary of the safety set, and the int C means the interior of the safety set. So we have two important definitions. So the first is a forward invariance set. So that's a key principle for control barrier function to guarantee the safety. So this safety set is forward invariant if for each initial state x0 belongs to C, and the future state will stay in the set. So this indicates the set C is a forward invariant set. Second is safe. So in the control barrier functions approach, they give a formal definition of safe. So the system is safe with respect to the set C. So if the set C is forward invariant. And in these slides, we show two typical design paradigms of the CBF-based control. So the first we call it safety filter design. So the key idea is that you can design a nominal controller without considering the safety constraints. So basically, this can be any feedback controller. It can be reinforcement learning controller. It can be like a nonlinear controller or neural net controller. Can be any normal controller. So once you get a normal controller, you can use a safety filter, so you can solve the get the updated controller to solve this QP problem. So this is a cost function. So U is a decision variable you're going to solve, and KLOM is a norm controller you have designed and subject to a constraint. So this is a CBF constraint to guarantee the safety. So the main benefits is here. So the safety is actually guaranteed by design, not like so in most cases we ensure the safety by like tuning the control parameters. Okay. So the second category is we call CBF CRF based design. Actually CBF CRF QP problem. So here is a cost function, so which is quite straightforward. So you can use a more complicated cost function like the economic cost. You can also like use a MPC cost. So here we have two constraints. So one is a CBF constraints. So it is used to guarantee the safety, and the second is a CRF constraint. So this one is to guarantee the stability. So in this control design, the safety and stability are guaranteed by design. So in the last part, I would like to introduce our research work in the safety critical control on the disturbances. Okay, so the fundamental CBF approach is unable to guarantee the safety under disturbances, but in real systems, disturbances are everywhere. Okay, so the first work is a robust approach. So we suppose the system is subject to some disturbances. So the basic approach is to consider the upper bound of the disturbance in the CBF design. So they define a robust CBF here. Okay, so because the impact of the disturbance have been considered in the CBF, so the safety of the system is guaranteed even under the disturbances. The second approach is to use disturbance observer. So they define a disturbance observer-based CBF. So the basic principle is, so if you know the disturbance, you can incorporate the information of the disturbance in the CBF. But the problem is, in most cases, we don't know the information of the disturbance. And we can use a disturbance observer to estimate the disturbance. So here D hat is the disturbance estimate. And another problem arises is the disturbance observer always have a estimation error. So we need to quantify the disturbance estimation error in the CBF. So here epsilon is the like a error quantification for the disturbance estimate. So this result is I think is have been done by the Professor Richard Marie in Caltech. So for this one, they consider the matched disturbance, and based on Richard Marie's work, so we find that in most cases, in many applications, the disturbance could be unmatched. So here is a UAV path following example. So when we like consider the candidate CBF, we design a very simple. So this is actually Euclidean distance. So when we calculate the derivative of the CBF, we can find that the disturbance appear in the derivative of double derivative of the CBF. So here we call the impact of a disturbance is unmatched disturbance. So we try to solve this problem. First, we try to use a disturbance observer to estimate the unmatched disturbance in the system, and we also need to like quantify the estimation disturbance estimation area. Like the high-gain state observer, we need to like consider the peak phenomenon during the transition of the observer. So we use some like a saturation equation, a saturation function to tackle this problem. And finally, we have the QP CBF CRF optimization problem. The key difference here is we use disturbance rejection CBF. We consider the disturbance information into the CBF and the CRF. And here is a simulation example. We implement the path following of UAV on the wind disturbance. We compare the performance of our approach with the basic CBF CRF approach and the robust CBF approach. So we can find the proposed control approach can achieve critical safety guarantee as well as very good disturbance rejection approach performance. The second theoretical work is focusing on the digital implementation of the safety critical control. So the major point is so in most autonomous and robotic systems, the control is implemented in a digital way. So the current CBF can only like guarantee the safety in the sampling instance. It can't like guarantee the safety between the sampling instance. Okay, so we try to use a sample data approach to guarantee the interval safety of the control system. So that's our second theory work. And we also do some applications. So the first case is called prescribed performance motion control. We only consider a second order system. So we use CBF to like guarantee the performance specification. So like if you have so if your control system have like a performance envelope, so we define the boundaries as CBF constraints. So here is a position control example of PMSM. So we do some like experimental verification and the comparisons. So we compare with baseline prescribed performance control and the baseline sorry baseline CBF control. So the result shows an improved transient tracking performance and with relaxed condition on initial state. That means in some cases, if your initial state doesn't satisfy the safety specification, it can finally enter the safety region. So the second case is about safe motion of compliantly actuated robots. So this case is concerned with rich contact robotic system. So like the robot assistant rehabilitation and wearable exoskeletons. So it's a position safety control. So this is robotic dynamics and this is actuator dynamics. And we have the control objective here. So we need to make sure the desired position trajectory satisfy the constraints. So it's a rigorous position safety constraint. And the challenge could include the first is unknown matched and unmatched time varying disturbances. And secondly, the order of the system is twice higher than that of the rigid robot. So we still use the disturbance observer to estimate the disturbance, and we quantify the estimation error, and we design a disturbance estimation based a high order CBF for the robot system. And here's a QP problem. So is the implementation is quite straightforward and quite computational efficient. And here is the experimental results. We also compare with the basic CBF approach and the robust CBF approach. And the last case study is about safe crane operation. So this is a real crane in quay, and the sorry, the safety problem here is that we need to make sure the unilateral swing distance should be rigorously controlled with a given region. And the challenge here is so because the payload is driven by a string, so it's a typical under-actuated system, and should follow the safety constraints, and also have the disturbance like the wind disturbance. So to overcome the under-actuated feature, we designed enhanced coupling control level function to guarantee the stability, and we use a composite state CBF to guarantee the unilateral swing disturbance distance safety. And finally, we use the disturbance observer to estimate the external and the internal disturbances. And here's a QP problem. Here's an experimental test setup, and I think we have a video here. So we have some comparison with the traditional control approach. This is a traditional like an anti-swing control. We can see here the tuning position and the swing angle. And then we add some disturbance. We can find the, like it's very difficult to reject the disturbance. The second approach we implemented is the baseline CBF CRF QP problem. So we can see it's safe, but the trolley can't return to the desired position. So this is a proposed disturbance rejection CBF approach. So you can see it's quite robust against the wind disturbance. And we also do some robustness test against the modal parameters like the length of the line. So this is a baseline approach, and this is a baseline CRF CBF QP approach. So this is our approach. So we do another set of tests to test the robustness against the mass of the load. So I think the results are similar. Okay, so I think that's all my presentation today. So here's our conclusion. We briefly introduced the background and the motivation of the safety critical control, and we introduced some like a safety critical disturbance rejection approach we have done recently. Okay, thank you very much.
Thank you, Jing. Thank you for your like insightful presentation. So we have like time for two short questions. Any questions? Okay, feel free to type in your question in the chat box. Oh, good. To and people raise hand.
Yeah, I think Zhongguo has
Zhongguo, do you have a question? So feel free to ask.
Right. Thank you. That's very interesting talk. I'm not quite familiar with the control barrier function, but we have a sort of a similar problem when we try to do optical avoidance. In particular, for example, we have time varying obstacles. As you mentioned, when we approach into the boundary of a specific set, the cost associated with the constraint will increase significantly. This will push back sort of the constraint to the center, let's say. But I was wondering, how can we possibly implement to switch from one set to another? Is there any recommendation to do so? For example, when we approach it to one boundary, but I want to switch to another operation point within a safety constraint.
Okay. Thank you, Zhongguo, for your question. So actually for the CBF control approach, we don't have this problem because the control law is obtained by solving the QP problem. So even like in the boundary, so if the state is on the boundary or outside of the safety set, it's okay. So you can still like find a feasible solution which can drive the system states inside the safety set. It's quite different from the like a barrier Lyapunov function, which use like a nonlinear gain to like guarantee the safety. Yeah, it use a different principle.
Okay, thank you. Thank you so much.
Okay, thank you.
Thanks, Zhongguo. Mian, so yeah, please ask your question.
Hi, Jun. Thank you for your presentation. So I see you design disturbance observer and then use the estimated disturbance for the desired control Lyapunov function.
Yeah.
I just wondering, when you design the control barrier function, you also need to use the dynamic mode of the system. Should we also use the disturbance estimation for the design of the control barrier function?
Yes. So yeah, we use a disturbance estimate in both the control barrier function and the control Lyapunov function, because the safety and the stability both will be affected by the disturbance.
And in that case, for example, if we have the large disturbance, so how can we, for example, if we use the UAV for the wind turbine inspection, in that case, we have very strong wind and disturbance. How do you guarantee the stability and safety for the system?
Okay, yeah. So I think this refer to another problem. So that is feasibility of the optimization problem. So like if the wind is very strong, right? The UAV is quite small, so you don't have enough power to reject the disturbance. Or in other words, in this case, the most important thing is to keep it safe. So you can't complete the task. So there are some like a contradiction between the safety and your control task. So we also have some work in hierarchical, like CBF control design. So basically, in this case, I think we need to like redesign our control task.
Okay, thank you very much.
Okay, thank you. Thank you.
Okay, thank you, Mian. So unfortunately, we don't have time for further questions, but I mean, if you have questions for Jim, please feel free to reach out to him after, the session. Okay. So, all right, let's move on to the second speaker. Dr. Umberto Montanaro. So he is currently a senior lecturer at the University of Surrey, and his expertise is in connected and autonomous vehicles, as well as other mechatronic systems. Okay, so his presentation is on application of deep reinforcement learning techniques to improve vehicle safety and performance. Okay,
Hi, can you hear me? Can you see the
Okay.
screen?
Yeah,
Can you see
yeah.
the screen? Good. So let's get started. Hi, I'm Umberto Montanaro, and I'm senior lecturer in control system within the School of Engineering of the University of Surrey. And in this presentation, I'd like to give you a brief overview of the use of deep reinforcement learning strategies that we have recently developed for vehicle control applications. Specifically, in this presentation, I would like to give you an overview of the use of the deep reinforcement learning method, here abbreviated as DRL, to the traction control problem for vehicle safety and path tracking problem for autonomous vehicle. Thus, this presentation is virtually split in two parts. For each of these applications, we will briefly introduce the corresponding DRL formulation and present some results. However, before presenting the methods, well, before presenting the DRL formulation and the methods, I would like to provide a brief overview of the DRL as a background. And the presentation concludes with a set of remarks highlighting what we have learned during the development of these strategies. Oops. Okay, stuck. Okay, in the case of the DRL, the controller, also known as agent, is a neural network that maps a set of observations gathered from the plant, also denoted as environment, onto the control action. The policy or control strategy is learned in simulation with the interaction of the agent and the environment, with the target of maximizing a cumulative reward function over a set of episodes, which are practically speaking a sequence of simulations. Good, so let's start with the first application that we want to consider in this presentation, which is traction control. In the context of the traction control, the controller adjusts the torque request, the driver torque's request to limit the wheel slip in order to maximize the tire force and maintain vehicle stability. Therefore, the functionality of the traction control is particularly important in the case of low tire rod friction condition, such as icy road. Indeed, in this condition, also a relatively small traction torque request can induce a significant wheel slip and potentially cause the vehicle to spin. And so the target of the traction control is to generate a torque correction to regulate the wheel slip to a given reference for preserving stability. In the literature of the traction control, there are effective model-based strategies such as a nonlinear model predictive controller, where at every time instant t, the torque correction is based on the optimization of a cost function over a prediction horizon. However, the tuning of the prediction horizon is not a simple task, as there is the need to strike the balance between the closed loop tracking performance and the real-time capability of the resulting MPC controller. Therefore, in this framework, we would like to design a real-time capable deep reinforcement learning strategy for the traction control problem, which also has the potential of outperforming nonlinear MPC strategy and its testing for icy road conditions. More specifically, in this work, the design and the testing of the controller has been carried out in simulation, but using a vehicle model experimentally validated on an ice surface. Specifically, the simulation case study that we have considered is the Zebra vehicle available at the University of Surrey. Zebra stands for Zero Emission Test Bed for Research on Autonomous Driving, and in this video you can see a test campaign that we have conducted for on an ice rig to the model design and the subsequent model validation. In terms of the formulation of the deep reinforcement learning for this problem, as observation, we have selected the longitudinal vehicle acceleration, the feedback torque motor, and an estimate of the wheel slip. Specifically, we use the average slip velocity error and the position of the acceleration pedal required by the driver. The control action is the control action is the torque correction required by the controller, while the reward function is mainly composed by two terms. The first term, here indicated as R performance, is considered for improving the closed loop tracking performance, and it is mainly composed by a penalty on the slip error and a reward on the velocity acceleration. Instead, the second term is a term that we have introduced for representing an expert demonstrator and penalize the mismatch between the torque correction generated by the DRL and the torque correction provided by a nonlinear model predictive controller. In this framework, the expert demonstrator is used to speed up the training, while the performance reward allows to improve the closed loop tracking performance with respect to the expert MPC. It is pointed out that both the deep reinforcement learning strategy and the nonlinear model predictive controller have been used. The sampling time for both the controller is 10 milliseconds. And in the case of the nonlinear model predictive controller, the horizon was selected as 50 step in order to get good tracking good performance in terms of tracking of the reference slip. However, with this selection of the control horizon, the resulting model predictive controller was not real-time capable on a D-Space micro outbox, that is the rapid control prototyping hardware that we use for testing our controllers. Instead, with the deep reinforcement learning approach, the resulting neural network was real-time capable on the same hardware. In terms of tracking, in terms of training, this has been done, as said, in a simulation where MATLAB Simulink has been used for simulating the controller, while the vehicle dynamics, for simulating the vehicle dynamics, we have used EVL, the DSM provided by EVL for a detailed simulation of the vehicle dynamics that we have previously estimated. This result, this slide shows some results. More specifically, we have compared three controllers. We have the deep reinforcement learning strategy. Then we have the expert nonlinear model predictive controller that I said before is not real-time capable with a prediction horizon of 50 steps. And then we have created a sort of real-time capable of version of this controller by reducing the length of the prediction horizon to 10 steps. The maneuver that we have considered is a straight line acceleration with a step input required by the driver equal to 100% acceleration pedal position. As we are operating the system on an icy surface, the road friction condition is very low, and all the three controllers are activated when the wheel slip exceeds 5%. That is also the reference. These results shows that the deep reinforcement learning algorithm provides the smallest overshoot and the smallest settling time, not only when compared with the real-time capable nonlinear model predictive controller, but also when we compare it to the expert nonlinear model predictive controller. And the reason is because of the additional terms that we have added in the reward function for improving the performance. And also the torque applied by the controller, the final torque that we apply on the vehicle is way smoother and less oscillatory when we use the deep reinforcement learning algorithm instead of the benchmarking control strategies. Now we can consider the second case study, that is the use of the deep reinforcement learning for path tracking. As we know, in this context, the target of the path tracking is to generate the vehicle commands such that a given reference path, possibly, for instance, provided by an upper level controller, a decision making or a planning, to counteract, and the target is to counteract all the vehicle uncertainties and possible nonlinear vehicle dynamics. In our formulation of the deep reinforcement learning strategy for this application, the control input is the steering angle rate, or the derivative of the steering angle. As also observation, we use the lateral error, its derivative, the heading error, and its derivative, that is the yaw rate error. In terms of reward function, it is composed by 4 components, where the first 3 are used for imposing a good tracking of the reference. Specifically, the first one is a penalty on the lateral error. The second one is a penalty on the heading error. And the third component here is a weight on the control effort. The last component that we have used in this reward function is again an expert demonstrator. And in this case, we measure the mismatch between the control action or the steering wheel provided by the deep reinforcement learning strategy and the one generated with an LQR algorithm. For this specific problem, we had the chance to do some experimental testing using full-scale autonomous vehicles known as Q-cars that are again available at the University of Surrey. The training for the deep reinforcement learning method again has been done in simulation using a model, a dynamic model of the Q-car that we have developed and experimentally validated. Here we have an experimental result where the target is to impose to the Q-car an infinity shape maneuver. And as we can see here, there is a good tracking of the reference path by using this deep reinforcement learning strategy. Furthermore, we have conducted some comparison, and the deep reinforcement learning method has been experimentally compared to a feed-forward feedback controller and two LQR solution. This two LQR solution is the expert demonstrator, and the second LQR solution that is equipped with a compensator of the steady-state error during cornering. Here we have some experimental results that shows the lateral error when the path that we want to execute is the infinity shape maneuver, and we can see that the deep reinforcement learning method provides the smallest tracking error. More specifically, the deep reinforcement learning strategy outperform the feed-forward feedback strategy, and also outperform the two LQR solution. More specifically, with respect to the LQR solution with the feed-forward compensator, the maximum error and the mean square root errors is reduced by 41% and 43% respectively. This improvement is even higher if we compare the deep reinforcement learning strategy, the results of deep reinforcement learning strategy, with the expert demonstrator, where this percentage increases to 53% and 60% respectively. Concluding, we can say that the use of the expert demonstrator has facilitated the learning, and the generated agent is able to perform well also when applied on a real plant. The performance terms that we have included in the reward function allow us to obtain controllers that outperform the corresponding expert demonstrator, and all the solutions were computationally efficient. On the contrary, as disadvantages, we have, of course, we knew that this kind of control methods are quite time consuming for the training of the neural network. And the success of the training a lot depend on the selection and the tuning of the reward function. And the last but not least, a key disadvantage here is that when the controller has been trained, and there aren't parameters that can be actually adjusted during its operation on the real plant. That's why now we are focusing on coupling deep reinforcement learning algorithm with the adaptive solution able to change online the gains or the weights of the last layer of the neural network to increase robustness against disturbances not considered during training. And this is the end of my presentation. Thank you so much for your attention, and if there are any questions, I'm more than happy to answer now or later. Feel free to email me.
Thank you, Umberto. Very interesting presentation. Any questions?
Can I ask a question, Umberto?
Sure.
Yeah. Hello, Umberto. So I'm Zhongbei Tian. I'm from Birmingham. So we met several years ago, and it's nice to hear your presentation. And my question is, so reinforcement learning, so it demonstrates that it's improve your traction system well. So, but I'm wondering, so is there still some gaps or challenge to implement that into the real application industry? Could you introduce a little bit?
That's a very good question. Actually, this is what I've shown here is a first work on this topic. Now we are collaborating with EVL, that is supporting some PhDs on this activity, and we had already the chance to test this strategy on an e-golf. And we have got good experimental data, and we have also had the chance to test experimentally the use of the deep reinforcement learning strategy coupled with an adaptation rule for changing the gains over the last layer to improve stability. So this what I presented today is just, if you want, the peak of an iceberg. We have done much more. And some you are processing experimental data that we have obtained with together with the company. Does this answer your questions? Kind of.
Yeah. So do they believe this reinforcement learning can definitely improve their safety? So for the future, right? So for different EVs applications, as you said.
Yes, it seems that there are chances to improve safety. Of course, up to now, for this formulation, there isn't any formal proof that the constraints are satisfied. We use the expert demonstrator to guide the controller, and in such a way constraints are fulfilled, but there isn't up to now a formal proof of mathematical proof that this can be guaranteed.
All right. Thank you very much.
Thank you.
Okay, Umberto, there's another question in the chat box raised by Mian. So can the uncertain tiles problem be generalized for terrain variation problem, rocky road, icy road?
Okay, in order to improve the generalization capability of the resulting neural network, what we have done is to consider a wide range of scenarios during training. For this, for instance, for this specific application, we have considered the different reference slip as well as different driver requests. So as a suggestion, in order to be, let's say, in order to generate an agent that is robust with respect to disturbances, is good to include during the training a wide range of scenarios. Of course, this will make the training, might make the training explode in terms of time required for the reward function to converge.
Okay, thanks, Umberto. So I think it's time to move on to our next speaker, okay, Dr. James Fleming. So James is a senior lecturer at Loughborough University, and he's working on intelligent vehicles and energy systems. His talk today is about MPC with parameter-dependent control policies with application to lateral control for road vehicles. Okay, James?
Absolutely.
Floor to you.
Thanks very much for the introduction, Bolly. Can I just check that everyone can see my screen and you can see and hear me okay?
Yes.
Fantastic. Sure. In that case, I'll get started. Well, yeah, so thanks very much for the introduction, Bolly. I think, as Bolly mentioned there, I'm James Fleming from Loughborough University. Today, I'm going to be talking a little bit about a new MPC technique, a robust MPC technique, which has parameter dependence in the control policies that it uses. So it's mostly a control-focused talk, but I'm also going to outline some of the applications of that and what motivated us to come up with that. And the applications really are to the lateral control of road vehicles, especially motorcycles and motorcycle stability assistance. I should briefly mention that this work is supported by my EPS Senior Investigator Award, which I hold at Loughborough University. And that's about safety critical MPC for autonomous systems, but also some aspects of reinforcement learning as well, which we're going to do a bit later in the project. So just as a quick outline of what I'm going to talk about today, the kind of headline, if you like, is that it's a robust MPC method. It's solvable in a single key P. So you solve a single key P online in order to implement this MPC. But specifically, it's for systems in a certain form, and it's this LPVA form that you can see on my screen here, where you have a state space system, and it's not a full nonlinear system. It's a linear system, but where the A matrix specifically can have a parameter dependence. So there's some parameter theta here, which is time varying, but we can measure it at each time t. And in the literature, this is sometimes used as a proxy for various nonlinear systems, or sometimes there are systems with specific parameter variations. And I'm going to outline a little bit our motivation for looking at that. But the kind of key novelty in the MPC that I'm about to present is that unlike previous MPC algorithms for this kind of system, instead of just optimizing over fixed control actions in the future in the MPC, so a predicted sequence of control actions, we're actually considering policies and optimizing over policies that are functions of the parameter itself, which reduces conservatism a little bit. So in terms of motivation for this, there's obviously a lot of research at the moment into autonomous vehicles of various kinds. When you look at autonomous vehicles, if you are doing steering control, you quite naturally get either LPV or quasi-LPV systems. That's the case even for about the simplest model you can come up with of autonomous vehicle steering. So I think the simplest model I know for autonomous vehicle steering is the kinematic bicycle model, which if you linearize it around a forward running condition, gives you dynamics that are something like a double integrator involving the lateral position and the yaw rate of the vehicle from the steering. But actually that double integrator has a gain that depends on the forward speed. So if you go forward faster, then it basically takes a smaller amount of steering angle to affect a certain change in position on the road. So even for those simple, very simple steering dynamics, we have a parameter dependence. We can also think of some more complex systems that have parameter dependencies like that. So a personal research interest of mine is to apply driver assistance systems, or perhaps I should say rider assistance systems for motorcycles. And when you're looking at motorcycle dynamics, actually they have significantly more complex lateral dynamics than, say, the kinematic bicycle model there, but they still strongly depend on forward speed. So if you're thinking about perhaps stability assistance applications for motorcycles or more complex autonomous systems for motorcycles, then really you need to think about how you take into account, robustly take into account that parameter dependence and that dependence on speed. And what I'm talking about today, actually, I mean, I'm mostly focusing on the control aspects, but we have a current collaboration with Professor Umberto Montanaro at the University of Padova in Italy. And what you can see on the bottom right there is actually his instrumented motorcycle that hopefully later this year we're actually going to go across and try some of our MPC controllers out on that in a real world test. So I'm quite excited about that. If anyone's interested in these stability assistance or path planning applications, actually a couple of my PhD students and postdocs just submitted some papers to this year's ECC and this year's IEEE Intelligent Vehicles Conference on those. I'm not going to talk about them anymore today, but I just thought I'd signpost that. Okay, so in terms of the actual MPC and the problem formulation, we're thinking about this LPVA system with a parameter dependence in the A matrix. That parameter dependence is itself assumed to be affine in the parameter. And our control objective in this kind of MPC is to minimize some worst case quadratic function, robustly minimize some quadratic function of the states and the inputs. Subject to some constraints, so we have some safety-related constraints involving the states and the inputs of the system. And we assume that the system itself is quadratically stabilizable by some feedback if you have a measurement of that parameter. And we also assume that for some value of that parameter theta, an observability condition holds on basically the A matrix and this cost function here. Okay, so we can see using the cost function, there aren't any unobservable modes in the system or anything like that. And the kind of novelty of this kind of MPC is that we're considering control policies that actually depend on the parameter. So if you are considering the motorcycle application, for example, the interpretation of this would be that the MPC controller internally in its prediction structure is actually trying to robustly plan different possible outcomes and different possible control actions for different speeds of the motorcycle. And we think that's important because if you have, for example, a sudden braking event when you are actually, trying to do some stability assistance, steering assistance for the motorcycle, then you want some robust guarantees that your controller is going to behave very well, despite that sudden breaking event or sudden thing that happens and sudden parameter variation. So by actually incorporating this into the structure, the controller can plan for these things robustly. This has some similarities to, so I'm calling this an affine in the parameter control policy, and it has some similarities to affine in the disturbance control policies, which I think probably several people here today are familiar with robust MPC and very familiar with that. And there's some similarities with that in the sense that the control action here actually depends on some future measurements or some future parameter that you don't know at the current time when you're planning, but you will know when it actually comes to that point in time in the MPC. And really the core idea, and we presented this at a paper at the CDC in Milan just in December, the kind of core idea that allows us to optimize over this control policy, these kind of control policies, is that you can actually come up with some equivalent autonomous LPV form of the dynamics for this system. So if we consider that control policy I had on the previous slide, this thing here, which has the parameter dependence on theta, these C sub K parameters, which we are optimizing over in the MPC, then there's a trick where you can basically concatenate these into a large vector that specifies the whole control policy and its dependence on theta at prediction time K. And then you further concatenate all of those parameters for different prediction times K in the horizon of the MPC into one large vector that specifies this whole control policy over a horizon. And if you do that, we found a mathematical reformulation of this where you can kind of take that parameter dependence out of the control policy itself and move it across into the sort of dynamic matrix of an autonomous LPV system. And actually the prediction dynamics of the MPC, the predicted future state that we get from this kind of control policy is exactly the same as you would get from this autonomous LPV system you can see here. And the little trick is actually just that we introduce this matrix S here, which itself has a parameter dependence on theta. And this matrix S actually kind of selects the relevant combination of these parameters defining the control policy at each possible time in the future, depending on what the value of theta actually turns out to be. Okay. And this is quite a nice trick because actually in the literature already, there's quite a lot of nice theoretical results and a lot of analysis of this kind of autonomous LPV system. So for example, one thing that we can do is that worst case quadratic cost that I mentioned a few slides ago, using this autonomous LPV formulation of prediction dynamics of this MPC, we can immediately write down some linear matrix inequality that then gives us an upper bound on this worst case quadratic cost. So we can write down this Lyapunov-like linear matrix inequality here. And this is something that we can actually solve offline before, at the design stage for the MPC. And we come up with this matrix W from that, and this W can give us a quadratic upper bound on this worst case cost in the robust MPC. Equally, if we want to handle constraints, we can consider things like the admissible sets. So that's, we've already heard, I think, in John Yang's talk about positively invariant sets of systems. There's quite a lot of nice theory on positively invariant feasible, that is, admissible sets for this kind of LPV system. And you can use, therefore, existing algorithms to develop admissible sets for this that you can then use to apply constraints in the resulting MPC controller. So for example, if you take a look at the book Set Theoretics, Methods and Control by Banchini and Miani, you will see that there are algorithms in there for this kind of system to actually come up with some invariant set for the system in the form V of multiplied by this X and these control parameters D is less than 1. And if you choose your control parameters within this set for the given value of X at a particular point in time, then you're guaranteed to satisfy all the constraints in your system forever in the future using this. There are other things we can do as well for constraint handling. So for example, you can also apply cube MPC techniques, which are quite powerful. I'm not going to outline those in this talk because it's a little bit too complex in the time that we have. But if anyone's interested in the tube MPC formulations of this as well, then we had a paper in this year's, well, I should say last year's CDC, and that was also published in Control Systems Letters as well on how to do tube MPC like this. So the final MPC algorithm that you get using this kind of technique is, as I mentioned, a QP. The way I've presented it here, we can present this very, very compactly, just using that admissible set that I introduced and using that quadratic upper bound on the cost. And then it's a very standard then MPC algorithm of, okay, you measure the current state, you measure the current parameter as well in this case, and then you solve the QP, you apply the control to the system and repeat. You can do some other nice things with this as well. So for example, if you are using the tube MPC formulation that was in that CDC paper, you can also apply like rate bounds on the system and things like that. So if your motorcycle has a limited acceleration and deceleration, and you want to exploit those limits, then you can do a pre-processing step in order to reduce the conservatism of this further. We have some nice closed loop properties. I think we've already heard a little bit today about safety guarantees, and I'm not going to go into this in huge detail in this presentation, but we can get robust guarantees of constraint satisfaction, recursive feasibility. And so basically, if this thing is feasible at the initial time, it should stay feasible forever and satisfy the constraints. And we can get some exponential stability guarantees for this as well, for this kind of algorithm. I've got one very quick example here, so I think I'm running close to my time. But when we try this out, I've got a very synthetic example here, comparing to a system that was already in the literature. Essentially, what we find when we apply this kind of MPC technique is that it gives us greater regions of attraction than any of the LPV MPC techniques already in the literature. Also gives some improvements in the closed loop cost as well. And in terms of computation time, for systems of say 2 to 4 states, we can get this down to the millisecond range in computation time as well. Yeah. So I'll summarize there and I'll wrap up. We've presented this MPC for LPV systems using this parameter-dependent control policy. It's restricted to systems where the parameter affects only the A matrix, but you do get some improvements in performance for that. So you get a payoff for that. It's motivated by motorcycle applications. Currently, we're implementing this into a MATLAB library, which we're hoping to share on GitHub very soon. We're going to be applying this on a real-world problem. Later in the project as well, because this is implementable as a single QP, we think we can use some existing results on differentiability of QP problems to try to embed this in a reinforcement word learning framework as well. So that's something else we're going to try to do, so watch this space. Anyway, thanks very much for listening, and I'm very happy to take any questions that anyone may have.
Thanks, James. Thank you for presentation. So do you have any questions? You can either raise your hand or put your question in chat. So hi James, I have a question. So your design required just to solve an LMI, to solve W by solving an LMI, am I right? So
yes,
is this LMI like guaranteed? Is the feasibility of this LMI guaranteed?
Yes. So the assumption that I had near the start that the system is quadratically stabilizable by some feedback, and this is some gain scheduled feedback as well. As long as this assumption holds, then we will always be able to find a solution of this LMI here. Yeah. I've missed a little bit out of this slide, which usually another thing we want to do here is reduce the conservatism of the resulting bound as well. And generally the way we would do that is to actually do something like minimize the trace of the matrix W subject to this LMI. But yeah, absolutely. As long as the system is quadratically stabilizable by some gain scheduled feedback, then we can always solve this LMI.
Interesting. Interesting. Yeah, any other questions? Okay, so if there are no more questions, I think it's time for like a short break, and we can, return to this meeting. Let's say by 25 past, so 5 to 11. So just 4 minutes break. All right. Hello, everyone. So now we are moving to our second session, which is about industrial and network session. So, I mean, during this session, we're going to have our industry speakers. Also, we have like some time for us to do some quick networking. Okay, so let's welcome our first industrial speaker. So Dr. Anastasis Georgiou. So, I mean, Anastasis is currently a senior control engineer with Nikola Motor. So Nikola Motor is an American manufacturer of heavy-duty commercial battery electrical vehicles, fuel cell electrical vehicles, and energy solutions. So before joining this company, he got his PhD degree in control systems from Imperial College London and was working on robust MPC and its application to intelligent vehicle control. So his presentation today is on energy management systems for fuel cell hybrid semi trucks. Okay, Anastasis, okay, I'll give the floor to you.
Thank you very much, Polly, for the introduction. And first of all, I would like to thank you for the invitation, and I'm very happy to see quite a few familiar faces around. So before we start with the presentation, I would like to give a brief introduction to the company. So as Polly mentioned, Nikola Corporation is a US-based company specializing in developing and production of zero-emission vehicles, primarily focusing in battery, electric, and hydrogen fuel cell trucks. Companies vision aligns with the growing demand of sustainable transportation solution, leveraging hydrogen and electric power to reduce carbon emission in the trucking sector. Our main objective here at Nikola is to revolutionize the transportation industry by offering sustainable alternatives to traditional diesel-powered trucks. Last, we also focusing into developing hydrogen infrastructure to support the fuel cell vehicle. Among other projects here at Nikola, as a senior control engineer within the advanced team control, I work on energy management strategies for fuel cell hybrid semi-truck, which will be my today's presentation topic. Before going into the problem, I would like to declare that this presentation will give only an overview of the problem formulation and framework, and will not include any solution simulation result and etc. So the problem description here is that fuel cell hybrid electric vehicles combine hydrogen fuel cells and battery storage to improve energy efficiency, reduce carbon emission, and enhance operation performance. However, the way that you effectively splitting the power between the various sources to optimize the power distribution is critical, especially on expanding the component lifespan and ensuring reliability vehicle operation. Focusing a bit on the FC high voltage architecture, you can see that we have the classic, the electric motor that is gonna be the one motoring the truck forward. We have battery as one source of energy, and then we have a fuel cell in current development. We're using a PEM fuel cell, where the necessary power is generating using hydrogen and liquid hydrogen. So the problem that we are facing is how you split the energy source depending on the power demand to improve the durability of the components and make sure that we effectively utilizing the energy that is required. So challenges that are in the EMS problem include power splitting optimization, balancing power between the fuel cell and the battery to ensure efficient energy usage and minimizing hydrogen consumption. determine the optimal operational point for the fuel cell, because compared to the classic hybrid vehicle, we have combustion engine and batteries. Now the fuel cell is our expensive component and not batteries anymore. So we have to make sure that we are using it in an effective way without minimizing its lifespan. Another challenge is the battery SOC management, maintain SOC within optimal limits to prevent overcharging or deep discharging, which affect battery health, and then ensure the battery can handle peak power demands and regenerate braking energy effectively. So people that don't know about regenerating when using regenerative power, actually motor also is a source of power which has to be stored in battery, or as you see in the figure, I also have another component that is called brake resistor, is where the power can be consumed when the battery doesn't have any space to save more energy, and is the worst case scenario, and we have that component for safety reason in case that battery is full, and then you have to really anticipate that extra amount of energy. And another challenge here is hydrogen consumption minimization to reduce the fuel cell usage, to improve the truck range and operation cost effectiveness, and manage transient power demand effectively to avoid excessive fuel cell activation. One of the main problems that we are seeing on the management of the fuel cell is that with high oscillation, we see higher degradation of the plates of the fuel cell. So we have to consider that in our problem and try to minimize the oscillation the oscillation of power that the fuel cell is proposed. Obviously, system longevity and degradation mitigation try to expand the lifespan of both fuel cell and battery, and also protect the other components of the system, which is inverters and motor. One of the biggest problem that we are facing on that is the real-time adaptability. So adapting energy management strategies based on the driving condition. We have trucks driving in urban environment, in highways, in stop-and-go traffic, and obviously those conditions affecting the way that you're gonna split the power distribution, and it's something that we try to evaluate, create different studies from different scenarios, and also accounting for variation in load, because we are working with trucks. So trucks can vary in the weight depending on the load. Also, you have the weather condition and then the road gradients that are factors that can improve the energy management strategy if they have been considered. Last, I want to talk about the elephant in the room, which is going to be the computational complexity. How intelligent can be your strategy is really affecting the computational complexity. And as other people mentioned in today's talk, computational complexity is something that we have to consider if you want to have a hardware implementation that can do the job in time. Moving on, EMS solution can be classified in 3 different categories. We have the rule-based strategies that actually based on the current, let's say, input, which is power demand, SOC, thermal loads, hydrogen level, and etc., are deciding how they're gonna split the power from the battery, power from the fuel cell, and what power can be consumed by the brake resistor. Another very popular approach is the optimization-based EMS, where here we can categorize a data group to dynamic programming, co-dragging minimum principle, and model predictive control. And as you notice for today's talk, a lot of people working on the MPC framework, because actually you can use prediction from the future to optimize your cost. And mainly what we are doing here, we are defining a cost function, and then you are listing your physical constraint and the performance constraint, and you try to solve a problem in real time. And then last, we have some learning-based approach, which include neural network reinforcement learning, fuzzy logic control, and generic AI. So one of the problems that we are trying now to solve is to create a model that is going to be end-to-end control, having a list of input, and then the modeling knowing what is going to be the output power split on those scenarios, and then try to solve the problem without going into deep on modeling or creating model for each of the subsystems. Few advantages that we can list on those three categories is that rule-based are easy to implement, require less computational time than the other two designs. But one main disadvantage on that is that it required expert people to classify all the scenarios, and in case that a scenario is missed, you can see that it's not anymore robust, and also it's hard to make it adaptable and change over time. So it has to be reconstructed at the beginning, and then we have the optimal base that it gives you a sense of optimality, but still, especially the model-based design require models that need to be designed, and also the computational expense. Then we have the model-based design that is quite flexible and doesn't need models, but still it needs a lot of time to train, a lot of data. And as for now, because we're still on the point that we are gathering data, is not enough to, let's say, train our machine learning algorithm to achieve the goal of energy management split. I want to also highlight here another, let's say, part of those methods, which is the predictive energy management. So how you predict the power demand that is going to come in the future, which is really rely on the environment, the driver intents, and then how you can construct, let's say, the future power demand as a sequence, which can be, let's say, using MPC method later on to minimize a cost function, is something that we're also looking into it. So environmental prediction, how to do the perception, listing few methods, but I will not go into this that. And then we have the virtual driver that it try to record the acceleration, pedal position, and brake position, and try to predict the intention of the driver, which is going to be fed to the physical dynamics of the vehicle and the control, which therefore going to give you the torque required, and at the end the driving the power demand that required to drive the vehicle in certain speed and torque. Last, for the people that are interested to dive into this problem, I will recommend to have a look at the reference model that MathWorks provides, that includes PEM fuel cell, battery, motor generator, direct driven transmission models and associated powertrain control algorithms that you can have as a start to simulate the environment, and then starting, let's say, for a rule-based control as a benchmark, apply your proposing method to improve the energy management problem. With that, I think I want to conclude. I want to thank you for your attention, and I'm open to any question if you have any.
Thank you, Anastasis. So do you have any questions?
Can
Okay,
I ask a
Zhongbei.
question? Yeah. Hello. Thank you very much for your great presentation from industry. So I saw there are a lot of debates about the hydrogen applications for heavy duty vehicles or vehicles. So is this cost economics? So considering compare with, I mean, so full battery heavy vehicles.
Okay, I will, let's say, not coming too much into the logistic of purchasing hydrogen, because it's something that is still underdeveloped, but I can focus on the advantage compared to the BEV vehicle, especially on the tracking application, to have a substantial range on a truck powered by just batteries. You're gonna need probably 2-3 tons of a weight of battery, which gonna also reduce your capabilities to load more on your truck. And then you have the hydrogen that is lighter, and then also it can increase your range by having the half of the sizing, let's say, of the batteries. And last thing that I would say is that also the efficiency of the vehicle with batteries, we are creating a lot of heat that it need to be also anticipated. So a lot of the power that is consumed by batteries is used to just cool the batteries. But with the fuel cell, we saw that we have so it's higher performance on the thermal load, which overall effectively give you higher range at the end of the day. So this is the stuff that I can highlight. Obviously, buying hydrogen now is more expensive than ever. So this one is questionable, and I cannot give you more detail on that.
Right. But so from industry, so you still investigate this technology and put that into the real applications, right?
It's not an investigation, at least for us. We have more than 200 fuel cells on the road. We have our station, and then we also give a solution to customers that they need just battery, because either they feel comfortable or they have the capabilities to charge the batteries on site. But yeah, it's a very new technology, and hoping that one's gonna give some traction to other people to move on. But as you see, a lot of companies, for example, big OEMs, Toyota, Hyundai, and others are moving towards that direction, either by using fuel cell or directly combust the hydrogen in combustion engine. It's something that is good to look forward to.
Yeah, yes, there are a lot of debates about that. So and from academia, so I really worry about the trends. I mean, so and yeah, so and the prediction is quite hard. Yeah, thank you.
Okay, and Anastasis, I can see you're working on this like heavy duty vehicle, okay, which you have like sufficient space for the hydrogen tank. But do you think it will be easier to transit to like family vehicles and using the same technology, hydrogen?
Well, we saw a few big OEMs that they are using small hydrogen tanks to just facilitate the the batteries. Obviously, for us, making more sense because we're a big truck, we have more space, and then actually improving a lot of the range. But yeah, it's still ongoing and on debate how that will work in commercial vehicles or the day-to-day transportation. But I saw a lot of potential in trucks or in trains that there's a lot of also movement toward that direction.
Okay, so thanks for sharing your insights. Yeah, I know. Okay, you are based in the US. I'm not sure. I mean, yeah, if it would possible to set up some collaborations in terms of project or I mean other sorts of like collaboration. I'm not sure it would be easy, but I hope after this event we could find some way to work together. I mean, in the near future, maybe some project. I mean, undergraduate and the postgraduate student research project could be
Sure,
possible.
it's something that we are looking into it. During summer, we are creating some openings for internship or giving a small task to a postgraduate student to look into that, especially the optimization problem that I mentioned. Is a lot of way to see the problem, so we are open to discuss that.
Okay, that's great. Okay, so let's move on to so next industry speaker. So Mr. Jingyu. Jingyu is a senior engineer with TfL Transportation for London. And before he was working at Network Rail, so he has like a rich experience. I mean, so with railway engineering. And I mean, I would like to say, so he's a hands-on engineer who not only works, I mean, in office, but also actively engage in field work. So today I hope, I mean, he can share us some like more practical experience working in the railway industry. Okay, and his presentation will be on embedding artificial intelligence for non-timetabled service operation. So Jingyu.
Yeah, thank you. Let's see. Not often. I don't use Zooms that often, so let me see if I can share my screen. Right. Give it a start.
Yeah, I can see your desktop.
Has it been shared properly?
Yes.
Okay. Is it all good? Right. Let's make a start. So, I'm so glad having this opportunity today, because my presentation today is not about something I know, but mainly about something I don't, like my absence of knowledge and understanding around artificial intelligence. So we have seen over the past decades, railway transportation has become increasingly automated. Many trains are now either driven or signaled automatically with train paths and schedules programmed into control center computers. As a result, the railway network operates with a reduced reliance on human intervention. These advancements, along with similar technological approaches, have significantly improved the whole network's operational efficiency. Here are some examples, which with some videos of reference regarding the technologies used in train control and signaling. And which is quite interesting one is this Elizabeth line, which is operating in London. And there is an auto reverse function at Paddington, which is very innovative. And the link is at the bottom. So for those who are interested, there are more descriptions, which I'm not going to go through a lot in more detail. And as we can see, AI has been continuously evolving. Questions remain about its role in safety critical decision making. Like Professor Yang mentioned at the very beginning of this conference, which is a really good point. So AI the role of AI in safety critical decision making, I think, is less explored, particularly in public transportation. The railway has never been free from risks, whether from external environmental factors or internal operational challenges. As a result, trains do not always run precisely according to their schedule. In some cases, delays cannot be absorbed or corrected by the already very busy system, leading to a cascading effect that spreads across the entire network. Not to mention those major instances that completely disrupt the timetable. These are situations where human intervention remains essential to restoring the traffic back to order and safeguarding freight and passengers' movement. My thoughts and questions are around how we will see, with AI more and more being integrated into different systems, how we will see AI replacing humans in handling those untimetabled operations or special circumstances. I suspect that compared to real-time frontline tasks, AI adoption might or probably have already started in second-line functions, such as timetable optimization, resource allocation, strategic planning, all possibilities. AI has the capability, we all know, of analyzing a vast amount of data, traffic records, recognize freight and passenger patterns, as a result, recommend optimal train schedules and routing. However, for those frontline tasks, although AI offers advantages in overcoming the limitations of human, for example, workload, stress, and fatigue, with the provision of sufficient computing capacity, of course, there are still some challenges on the other side of the coin, like the development of risk assessment frameworks, approval and assurance processes to deploy AI safely and reliably, as well as compliance management with the local legislation, alignment with the shared social and ethical values. These areas, as I said earlier, I believe are less explored, and this is really, I hope today's discussion can provide me with the opportunity to expand my understanding, connect with the experts like you in this field, and gain some valuable insights into the approaches to facilitating the AI future application in public transportation. So far, I can see two practical challenges. First is about the risk. There are some early stage and still developing ideas about using AI to mitigate safety risks, such as detecting objects on track, operating equipment, and other infrastructure defects. Such attractive and widespread ideas have their own drawbacks. For example, Professor Sidney Deckard argues new technologies may replace an existing risk with another one or move people from a risky workplace to another place, leading to new safety issues and pathways to failure. The second one I do see is the scarcity of instant data presents a challenge for training and testing AI models. The proportion of instant delay minutes or number of instances compared to the normal operating minutes is extremely small, meaning that AI systems have limited real-world failure scenarios to learn from. I don't know, this lack of high-quality training data could how to mitigate the impact, the impact AI's ability to accurately predict and respond to rare but critical disruptions that could potentially undermine its reliability in safety critical applications. And there is a final thought from me is looking ahead. I guess adopting AI in rail transportation's automatic and autonomous operation is a key enabler for enhancing efficiency and ensuring sustainable network performance. AI integration could support a more complex, coordinated, and comprehensive railway system by optimizing infrastructure and rolling stock maintenance, managing traction power flow, and advancing decarbonization efforts. Moreover, we can see there are some more elements I put here. AI-driven real-time decision-making could enhance operational resilience, improving the network's ability to respond dynamically to disruptions while maintaining service reliability. These are so many possibilities, and we are here to make those things happen safely and reliably. And I really hope if anyone today, and this is the last slide of my presentation, and I hope anyone today has any ideas, could have some, like, we could have some collaboration on the policies and risk assessment standards, those are mentioned elements. At the moment, I try to work with Bo Li and later Dr. Tian and Zhongbei to see if we can initiate some projects. Please let me know if there are any other opportunities that we can collaborate. And that's the end of my presentation. Thank you. I hope it's not too short.
Thank you very much, Jing. So very good time management. So any questions?
Yeah, thank you.
Oh yeah, sorry.
Yeah, thank you. Thank you for your presentation. Yeah, it's me again. So I would like to ask, so I mean, so using AI to solve, I mean, the safety related issue, is there some restrictions? I mean, considering the whole TFL, so you have a lot of responsibility to trains, to network, and to infrastructure. So are there some very complicated considerations?
Yes, well, this is a very important question I'm facing, and I don't have an answer because at the moment I don't use my colleagues. We don't use AI to make safety critical decisions, which means the AI is not making decisions on safety critical posts because we are shouldering the responsibility as a public transportation organization. So we do see like AI offering options, but not on safety critical post. So AI does offer like different ideas, maybe solutions, but I still need people to review and the outcome of the AI as well as the input to the AI. And so it's at the moment it's very kind of an early stage. If I try to use a better word. So I think it's at the moment I think it's more like how we are going to collaborate with AI, not being replaced by AI. And as I have seen, I mentioned in my presentation, the main thing is how to assess the risk and how to, even retrospectively speaking, is how we boundary the responsibility. These are all the considerations and what kind of legal requirements we need to, because whatever decision we make has passengers' life behind it. And before we are confident on the AI, I don't think it's going to replace, or before there is assurance or compliance process in place, I don't think the AI would replace people. And that's why I really hope to look at the development, not only just technical, like how the AI, the technologies, but also the policies and how we mitigate the risks.
Yeah.
I hope my explanation is all right. Sorry, it's not easy for me to pick the right words to describe my idea, but I hope I conveyed my message.
Thank you. Any other questions? Okay, so yeah, as Jing said, so TFL, the UK-based company, so I believe there will be more like opportunities, and there shouldn't be too many barriers for us to collaborate. So I hope everyone can benefit from this session and maybe to seek some possibilities to working with Okay, so yeah, I think it's time for the next step, which is like a networking session to the main room. So yeah, I apologize for having to make this session like so very compact. Okay, but I mean we do like behind the schedule. So I mean, of course, I hope you already have time to know each other, at least know some colleagues working, I mean, in this area. And I mean, we can definitely continue, I mean, this conversation beyond this session. Okay, now let's so move on to the third session of this webinar. So, and in this session, we're going to have two another speakers. I mean, and their research are focusing more on the sustainability mobility. I mean, sustainable mobility part. Okay, so next speaker is Dr. Zhongbei Tian. He's a lecturer at the University of Birmingham, and he's primarily working on railway system, energy system decarbonization, okay, but also covers some other transport modes. His talk today is about connected and coordinated train operation and traction power supply system for decarbonization. Okay, Zhongbei?
Thank you, Billy. So
please.
I have shared my screen. Many thanks for your introduction. So I'm very glad to give a brief introduction of my research about coordinated connected train operation and power supply networks. So in this talk, so I will briefly introduce my research group and background of my research, some challenges, and then I focus on 3 main topics for railway decarbonization. So including digital twin, including the train operation and control, and also smart grid transport energy systems. So my team, so at University of Birmingham, so we have a large research center, so in railway research and education. So currently, so we have built this group over 50 years, and we have a group of over 160 researchers. Regarding the transport or railway, so decarbonization challenges, I think so most of previous presentation also covered that. It's not easy for transport decarbonization, and for railway is in general is already energy efficient way to travel, but there are still a lot of challenges. So for example, in the UK, the railway electrification rate is still very low, so it's below 40%, and still a long way to go to the full electrification. And to electrify the railway system, so there are some challenges, including the peaky fluctuating power flow, substation power supply, because this is heavy duty vehicles should require a lot of power for acceleration, and this kind of electrification network also cause the substation voltage fluctuation, which reduce the resilience reliability to power these vehicles. And also, as I said, railway is not the only solution. So we have to work with other transport modes. And I think that is our networks trying to do to future mobility. So how to collaborate with different transport modes to achieve the net zero to transport. And for railway, there's also a unique section. So because I'm not only doing control, I'm more or less a system engineer. So because in railway, there are more collaboration or coordination with infrastructure. So for railway, it's rely on the overhead line system, for example, and a lot of track problems, and the railway train-to-train communication, and compare with other transport sector, I think more coordination, more collaboration should be looked at in the railways research. Yeah, and that's why based on this railway system, I propose generally 3 main methods to decarbonize railway system. Digital twin for energy system is the first one. So to properly model the railway energy system, not only model the vehicle itself. So we call this single train motion simulation, so traction, so modeling. And also we gonna model the multiple train power networks. And this enable us to understand the multiple train, so coordination and the interaction with each other, and also the interactions with the AC power grid. So like here, so because to power the railway network, we need so traction substations connect with the national grid and to supply this reliable power network. And to achieve that, so we built up this so energy system modeling. And so with that, so we are able to analyze the power flow, so energy flow. So in these 4 layers, so from the AC network layer to substation layer to catenary layer, so within the railway and also the train level. So for considering the traction system, motor stuff, and also there are a lot of regenerative braking energy. So when train is braking, and this energy can not only be used by the train itself, and also can be sent back to the catenary system and sent back to other vehicles and sharing this energy. And also the surplus regen energy can be fed back to the AC grid. And also this also about coordination, about the sharing, the unused energy and for better usage. And based on that, so we have developed a kind of digital twin, to emulate the railway environment, including the timetable stuff, including the traction power network, train voltage and power. And here is a brief demonstration of the train simulation. So here you can see that the multiple trains running at a given railway network, and we know the speed, we know the location, and we can calculate the power, substation power, and the energy flow, and also the efficiency and regenerative braking energy losses. And based on that, we can do a lot of control strategies to improve the control, improve the operation. So for example, we can improve the trajectory, so train speed profiles. So I think for most transport sector, we do a lot of work. So how to optimize train powers, so trajectory, and railway can be simpler because there's a given route. And also we model and analyze the communication because we want to achieve the train-to-train communication and the train-to-infrastructure communication, so to understand the whole system performance. And here is some results. So from the train control and optimization, so we have developed the smart drive technology, and it's basically trying to optimize the traction rate, for example, and cruising speed and coasting speed and braking, and to meet the train timetable and to arrive the station on time. And we have published some papers, and also we have been working with Edinburgh Tram to implement this smart drive strategy. So we did some field tests, and from the result, we find with a given optimized train driving control, so we can reduce energy consumption by 9.2 to 17%. Okay, so we did full field tests in Edinburgh Tram several years ago, and we got this. And in the next stage, we found energy saving is not from only one train, so it can be the whole network, and the whole network's energy efficiency optimization. So we have to rely on more smarter technology. So here we introduced the AI technology for coordinating the transport operation. We developed the data-driven methods and to estimate the substation energy from the substation level, and then we can change or control the timetable a little bit and dwell time. And to shift the train a little bit and and shift the train, so acceleration and braking a little bit, and then so we can improve the whole system, so energy efficiency by reducing the transmission loss and increasing the regenerative braking energy receptivity. And so with AI, so definitely, so we have a better result. So using this data-driven method, so we only use 0.3% of conventional simulation time, but we achieve 99% accuracy. So based on this model 3, model, and also we reduce energy consumption by 13%. And also, so this is kind of a comparison. So we compare with the existing train control strategy and the traction only optimization result. And the final one is the whole system AI-based optimization, so which achieved the best result to reduce substation energy by 38%. And also, so currently, so I'm working on an EPSRC project and to further develop this coordinate train operation and power network. So in this project, so I try to coordinate the train, so running train model with the traffic model. So for railway traffic model, so and considering the signaling system, so to giving some constraints to each vehicle. Okay, so to let them not be very close with each other for safety reason, and also to meet the speed limits requirement and other requirement. And also we connect with power network simulation, so the third model. And so by developing this coordinate network, so with same clock, so we are able to achieve some data exchange, so in real time, and send the dynamic control strategies to each vehicle. Yeah, and that is very challenging part. So because for example, we're gonna assess the traction network, power network information, and then we convert that information so for the train control directly and tell the train so what to do. So considering the existing traction power network situation. And here is a simple demo. So here, so we just want to demonstrate that. Okay, so with a given speed reference, so now we are able to change the train, so driving controls and to follow the given optimize the train speed trajectory. And the next step, so we're gonna further implement multiple train interactions. And this is a timetable for one train. So you can see that from distance 0 and to 40 kilometers in the end, and with the given time, so in the y-axis. And the last piece is about smart grid and transport energy integration. So this part, so we're gonna consider some more infrastructure-based energy sources. So with the coordination, we consider the renewable energy system and energy storage. So wayside, so infrastructure-based, and we want to coordinate the wayside, so energy supply facilities, so with the railway system. And this enable us to control, for example, the power converters, okay, for both AC and DC railways. So consider we are using, yeah, so we trying to build this control center, and the control center can collect the operation information, so from the vehicles and also from renewables, energy storage, and finally, so send the control strategies to not only the energy storage, charging, discharging control, and also control the vehicles in real time. And in the lab environment, so we are building the station energy hub, so with hardware in the loop to demonstrate these control strategies. Yeah, considering the time, so I'm gonna briefly introduce this is one result. So we did several scenario case studies, so with energy storage and with renewable energy generation. So here, so we can reduce the peak power demand and also improve the energy efficiency. So with this giving control strategies. And also we are also working on an innovative UK project and to demonstrate this control. So energy storage, so energy management strategy. So for the one railway, so set, okay. And here is the lab demonstration. So we got power converters set up, and we're gonna need to control so 4 main converters, so 2 AC/DC and 2 DC/DC converters, and based on the information from the trains and from renewables. And we have a supercapacitor so set up, so which is to respond the train traction and demand, and also to collect regenerative braking according to different situation. Yeah, so that is a general so introduction of my research. I think that in the future, so to achieve net zero, so definitely I really want to work with also other transport sectors and to learn from each other and also implement the multimodal transport collaboration and the coordination stuff. So considering for transport, so we aim to move the passenger and goods safely and on time. So railway cannot solve this problem. So we have to work with other heavy duty vehicles and autonomous vehicles, road transport, and so on. Yeah, and I'm very keen to working with you, and many thanks for the ACE network for the invitation. And this is my contacts, and happy to host your visit to Birmingham and discuss some opportunities in the future. Thank you.
Thanks, Zhongbei. Thanks for sharing your insights. Do you have any questions? So I wonder, so yeah, if no one asks question, I have one question. So I wonder when you do this, because you use battery storage to regenerate the braking energy from the train, am I right? So do you have any safety concerns when you control this? So because I guess the power withdrawal could be very high, and so do you consider use any control approach to take into the safety into account?
Yeah. So when we do this lab test, there are a lot of protections. So this is general. So for the electrical circuit protection stuff. So for example, so we have a lot of circuit breakers. So if your current is over the circuit breaker limitation, so gonna trip this circuit. So we got this is I think kind of conventional protection system to protect the device. And also for the supercapacitor energy storage, it has its own protection system. So to protect the energy storage when generally current. So when the current is there's some high current happens, or by short circuit, for example, so it's gonna trip the circuit and protect it. Yeah, but I believe maybe there will be some smarter protection schemes, so with more controls and smart decision making stuff.
Yeah, yes, I believe. If there's some opportunities for people, to contribute, these aspects from algorithm. So this side, this would be quite interesting for people working in control. All right, so Jingyu, so I see you raised a hand. Do you have any question?
You are muted, Jing.
Yeah, so sorry, I'm not good at Zoom, but I do agree on that question, which is quite important. That was what I was thinking is, the safety concern, because we are connecting auxiliary components to the existing traction power system. And I do see the control and the protection is a key concern. But my question wasn't about this, was regarding the previous slides on the coordinated system. And it's quick question is how the systems, what kind of sensitivity analysis, how the benefit would change depending on different levels of system automation. We know many trains or many networks are not fully automated. Some of them are still very low level of automation. So if the signal is still based on the line-side signals and lack of a high-level automation, how would this affect the benefits?
Yeah, thank you very much. So this is a very good question. And actually, so in the UK or across the world, so every railway network are different. So that's a true challenge because so railways, we have legacy systems. So I mean, so in the south or in the north area, so the railway network got different trains, so with different communication system, signaling system, and different infrastructure. So some substation got, I mean, so for example, communication, and SCADA, and maybe some very old substation don't have this kind of facility, and this really difficult to implement that into the real world. And what we're gonna to do, so from academia, I'm going to develop a generic model, so very generic, so digital twin, so which can cover the most scenarios in railway environment. So consider different train parameters and different power supply characteristics, and then so in this generic mode, we can test the different automation control strategies. And next step, so when we introduce that into the real applications, then what I need to do, I just need to set up different rolling stock parameters, and then so to give some bespoke control strategies considering the existing facility. So I think this is what I'm trying to do. And also, I think for TFL, so there are more than 10 different networks.
Yeah.
So some routes got advanced communication signaling, some routes got advanced trains, and this railway system is really a long-term investment, and we will never get a brand new system with everything there. But from the digital environment, what I can do is I can cover most scenarios in the model, and then try to implement that to give bespoke and strategy for different networks. So yeah.
Thank you so much. Thank you.
Okay, thank you. So now I think it's time to move to our last talk, which is given by Dr. Mahdieh Sadabadi. So she's a lecturer at the University of Manchester, and her research area is mainly about cyber-physical energy system, including microgrids and EV charging networks. Okay, which I mean could clearly support integration of transport and energy systems. Okay, her talk is about microgrids for resilient EV charging and future electrification.
Thank you, Bolly, for the introduction. Hi, everybody. As Bolly mentioned, I'm going to talk about the role of microgrid for supporting resilient EV charging and future electrification. What makes this talk different from the others is I'm going to talk about the challenges of future electrification from the power grid operation. As you might know, like the power grid has faced the dual challenges in our transition to net zero. On the generation side, we have had a large integration of renewable energy resources such as photovoltaics and wind. So these renewable energies usually have weather-based, they are usually weather-based. So we have like some stochastic behavior in our generation that's unlike the traditional and conventional power grid with synchronous generator. Also, the large integration of renewable energies into power grid have introduced like some technical challenges such as reduction in inertia of the system, meaning that the robustness, and we have a stability issue. In our language, it means that we have stability issues. So these challenges are from the generation side are more or less met by the UK grid operators and grid operators around the world. And now we are in the situation that we can say we have a relatively reliable UK grid. However, we are anticipating that there will be some new challenges because of like the electrification of transport and heat. So the focus here will be on transport electrification and more specifically EV. The challenge will be about the major and massive increase in the demand side. And also like EVs are not the typical loads we have. So there are controllable load. They introduce some challenges. At the same time, they provide some opportunities. For example, by smart charging, we will be able to reduce the peak demand and vary the demand to better match supply. I will explain this later in the next slide. And also, because they are open to human intervention, so they also introduce some new risk as well. In terms of the scale of the scale of electrification, according to the UK government ambitious target for electrification of the transport, the plan is all new cars and vans to be zero emission by 2035, that's within 10 years. So now the main question is, does this match the UK grid capacity or not? So in order to answer this question, I'm going to provide you with some forecasts by National Grid ESO, National Grid Electricity System Operator. According to forecasts from National Grid, if all EVs in the UK were to charge simultaneously in the late 2030, they would require over 200 gigawatts of the total power capacity. In order to have some ideas what's the current or power grid capacity, I think it's right now is around 80 gigawatts. So what you want to say here is this is the worst case scenario. It's not even the worst case scenario. That won't happen. But the forecast also says even if 1% of EVs in the late 2030s were to start charging at the same time, that would create a load step of over 2 gigawatt, which could have a massive impact on the operation and stability of the grid. So that seems like we're gonna have challenges. The challenge is, it seems like the demand and the supply won't match in future. That means blackout. That means the stability issue from control perspective. So this figure also shows the National Grid future energy scenarios, and it shows that under any scenarios, there will be a 50% increase in peak demand in the UK by late 2030. So now it's like how we are going to support the transport electrification. So this also, this figure shows like the feature of EVs, because as I said from the beginning of this presentation, EVs are not the typical loads. They are smart loads. They are control loads. So in order to see how EVs, smart charging of EVs can help us to reduce the peak demand, I'm going to present this result for you. First, consider this black figure that shows like the typical demand excluding EVs during the 24 hours in UK or more or less in every country. So during the morning, the demand is low. Around 6 to 7 p.m. when people, 6 to 7 a.m. when people get up, so the demand increases. When we are at work, like the demand is more or less constant. And in early evening, when we come back home and we start to turn lights on, cooking, heating on, so the demand increases. So that's the typical power demand in 24 hours. Now, we want to consider the demand when we have EV charging, but this EV charging is not manageable, is not smart, we have dump EV. So that is like the green figure. The green figure shows that in the early evening, when we come back from home, we put our EVs to be charged, and there will be a huge demand because of the EV. And as I said before, that's beyond the UK grid capacity. So now we want to see how we can use the features of EV, such as like V2G or G2V capability. So what we want to see is how we can make the timing of the demand more flexible and how we can use the storage capacity in EV batteries. So ideal situation is the figure shown in orange. What we want to do by using EV and features of smart charging of EVs, we want to make the demand more or less constant. For example, during early morning, when the demand is low and there is a spare capacity in the UK grid, is the time to charge EVs. And by doing that, in the evening, when we come back home, we don't need to charge our EVs. And also this figure shows something interesting. It shows that when we have EVs and we charge them in a smart way, we have like this feature that we can even decrease the peak demand when we didn't have EV. And this is because of like this V2G capability is transferring the electricity from the battery of our cars to the grid. However, this cannot be done manually. So we need to do it in automatic way. We need to find a way to control the EV charging in a smart way. So the focus of my talk is not on that area. I'm going here to provide another solution that does not fully solve this problem, but support the transport electrification, and is a solution that does not depend on UK grid. It's a solution that's independent of the grid, and the solution is microgrids. For those of you who might not be familiar with the concept of microgrids, microgrids are defined as the small-scale interconnected loads and distributed generation units. They have this feature that could be independent from the grid and support their own load. And when the grid is subject to some stress, such as like during the peak demand, they can be connected to the grid and support the grid. Different organizations such as like US Department of Energy, SIGRE working group, that's similar to IEEE working group, but is more practical. And IEEE standards all define microgrids in a similar way. So in order to show you the concept of microgrids is not a theoretical concept, there are a lot of real-world implementation of microgrids around the world. This slide shows some examples. So in England, we have a lot of small microgrid, but there are small ones as far as I know. So, but in Scotland, we have this Isle of Wight microgrid, and there are a lot of them everywhere nowadays. So as I said before, they are not going to fully solve the problem of future electrification, but they are going to support it. So why these microgrids is the concept is relevant to our community, or why I'm presenting that. The reason is like control system. Microgrid, the brain of microgrid is control system. And in other words, like control system are core to microgrid operation. The control of microgrid is usually based on a hierarchical control. We have 3 layers of controller with different communication network and different control bandwidths. So each layer has its own objective and also its own challenges. So we have the top layer, that's the tertiary control, that's responsible for energy management based on weather forecasts and energy markets. So it's usually a centralized control, and it's the slowest control unit. We have secondary control in the middle layer, usually distributed and responsible for power sharing among distributed generation units. And we have the bottom layer, that's the primary control, usually decentralized and responsible for standard voltage and frequency control. And they can be connected to the main grid by making this switch closed or disconnected. Also, microgrids could be connected to each other, and in that case, we have a network of microgrids. So in terms of the challenges, so in tertiary control, as I said, it's responsible for energy management. So usually the solution is based on optimization, MPC stuff. So the challenge usually is like we usually don't have accurate models, and we need to integrate some data. For example, the data about like the weather forecast. So optimization, complexity, uncertainty in the system, and integration of market and economic is also a challenge. We have cybersecurity issues in the tertiary control. In the secondary control is usually based on communication network. We have the challenge of communication constraint, latency, cybersecurity. And finally, in the primary control, we have the stability issues. So especially if we have some nonlinear loads such as EVs. So one of the challenge, for example, is regarding to plug and play control, because the generation is not fixed. As I said before, they are weather-based. They are going to plug in into the system and plug out into the system from the system. So the centralized design of the controller might not be relevant here. So like right now, the solution, one of the solutions that's common in control community is based on passivity-based method, saying that if each generation unit is passive, then they can show like the whole system is passive, more or less like the idea is like that. But the issue is it's conservative. So therefore, like National Grid, as far as I know right now, is looking for solutions that are less conservative than passivity. So we have a lot of power converters in that are interfaces. So they have a low robustness with respect to disturbances, and that also makes another challenge in the primary control. So in general, microgrid could be a low carbon resilient and economically viable opportunity for supporting transport electrification. However, their successful implementation will require a sophisticated control and optimization algorithm and robust cybersecurity measures. Thank you for your attention.
Okay, thank you very much, Mahdieh. Thank you for your presentation. So yeah, do you have any questions?
Can I ask?
Yeah, sure.
Yeah, sorry, can I ask a question? Sorry,
Jing, go ahead.
Yes. So, thank you for this presentation. I do have two questions actually. One is a simple one. One is a little bit more, I guess, more complex one. So the simple one is, how macro is the macro? Is would you think bus terminals, the electric bus terminals, could be an example for deploying this technology or this topology of control system? And the second question is regarding the specific plot. When we are shifting the charging load to the evening hours or to the early morning hours, would how would this impact the social and ethical values of people seeing the car and their life pattern? And the example came up in my mind was we use cars sometimes also have emergency functions. If I'm not charging my car at evening, how am I going to respond to, for example, my family's emergency in Manchester? If I'm based in London, I wouldn't be able to drive that far.
Okay,
thank you. Yeah, that's our two questions from me. Thank you.
Yeah, thank you for your question. Regarding your second question, I think like this solution is what I show you is like the ideal. So it's not like the current solution, because we kind of have like 10 years time to solve this challenge. So there are many aspects that need to be considered. As you mentioned, like the ethical aspect, social aspect needs to be considered. And I think that's why like right now, National Grid is struggling with this problem, and they are trying to find a solution. And I think that's the reason I wanted to share this one, because I wanted to share like there is this challenge as far as I know, and perhaps like control community can contribute something like by providing like a way, like, because this ethical and social or other constraint is a kind of another constraint into our optimization problem. So at the end, I think we need to solve an optimization problem, hopefully it's feasible, with a lot of constraint, and not all constraint on technical constraint. Some might not be, like as you mentioned. About your first question, can you please repeat it?
Yeah, it's how macro is the macro. Would you see, because you also mentioned the challenge, like EV charging is a non-linear load and it poses a challenge. Would you think like because if 10 years later all the buses are replaced by electric bus, And would you think like the bus terminals, each bus terminals be able to accommodate the implementation of this control topology to charge the electric buses?
I'm not sure about that, to be honest, because I think no, it's not that easy because, so like EVs, the behavior is like constant power loads, and then the way they work is like a kind of negative resistance. So meaning that like we cannot assume like we have like a microgrid with all EVs. We need to have, at least I'm talking about like the control perspective, we need to have like some resistor loads into the system as well, such that like we can make sure the stability is guaranteed.
I see. Thank you. Thank you.
Okay, it's very nice discussing. So any other questions? Okay, so if there are no further question, I think so we're moving to the end of today's webinar. So yeah, I'd like to thank everyone for your participation and thoughtful questions, and a huge thank you to our speakers, of course, for sharing the insights and making the presentation. So, and I apologize for the delay. So yeah, I hope today's event, is not just like okay, we have the event, then okay, we stop conversation. Okay, so I hope this will be the start of many fruitful many like collaborations in the future, and we can continue conversations like today. Okay, so beyond the session. And I want to remind everyone who registered, okay, you will likely to receive a short follow-up questionnaire. So we appreciate, okay, the AC network would appreciate your feedback. And I also want to remind you about the two upcoming early career research event. So in the following weeks, I think next week and the week after. So focusing on control AI and clean energy. Okay, so I think both are highly relevant to our research. So you're welcome to attend, and if possible, promoting the event. So one last thing is there is like a larger in-person event taking place in Oxford in March. So it's on 24th and 25th. So, and you are all welcome to attend. So, okay, and I hope to see you there. So, well, okay. So thank you again. And I hope you, have a great rest of the day.
Thank you. Bye-bye.
Thank you. Bye.
Thank you.